sacred institutions. Bedroom eyes, they call them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depths to satisfy.
So I've got to start off by giving you a little bit of background. I studied physics for 4 years, during which time I did a lot of problem sets and almost no chatting up, which might be familiar to any other physics students out there. But one thing I did notice is how the subject is just filled to the brim with innuendos. It seemed that everywhere I looked there were hot, dense bodies, fully degenerate limits, or just references to wet and dry friction. So I wrote a whole bunch of physics-based chat-up lines, more as a kind of ironic, haha, I'm gonna die alone type exercise than as a genuine attempt to attract people. I mean, in all honesty, I'm kind of a prude and would never use any of them in real life, and anyone who does use a chat-up line in real life is probably quite sad and or unoriginal. At least, that's what I thought, until I got elected president of my college's physics society and suddenly found that I had to make a speech. And so it was that I ended up making jokes about spontaneous emission and quasi-flow in front of an audience of educated and venerable professors, in black tie that didn't really fit. They were dark times. Anyway, this would have just been another side note in a life filled with tragicomic, sitcom character type events, except that I still had all the chat-up lines, lurking in a dark and musty corner of my computer. And I still had a whole bunch of physics knowledge, lurking in a dark and musty corner of my brain. And I wanted to demonstrate to the world that I've got the moves as well as the looks. And I thought maybe, just maybe, some of you out there are trying to seduce physicists, and you could use a little help. Or you're trying to learn physics, and you could use a little light relief. So over the next few episodes, I'm going to explain some ideas about physics, using my chat-up lines as a guide. This is going to combine my 4 great passions in life, I think. Awful puns, awful flirting, awful physics, and blathering endlessly on about stuff that no one could possibly be interested in. So there are 2 massive disclaimers here to begin with. I'm going to try and be as correct as possible, but I have to balance that desire to actually communicate something. The physicists among you will know that our field is a set of approximations to reality. Now, they get better and better, and they can get more and more detailed and complicated. But there is always value in explaining things in a simplified form. After all, when all of you went to school, first you learned Newton's laws, and then later on they explained general relativity, if you got that far. Now, relativity is more correct, but you can land men on the moon just using Newton's laws. Even if they're only approximately true, it's good enough to help us understand. So if I'm ever guilty of being only approximately true, I justify it by saying it's the only way we can ever learn. And also, I'm just a lowly graduate, so there's always a chance that I'll make some mistake, or say something you might disagree with. And ideally, I want this to be a dialogue. If I go too fast, too slowly, or make no sense, please tell me. And if you have any questions you want to ask, please ask them, and I'll do my very best to answer. Email me, at me, details will be at the end of the show. We can sort it out, argue about the best ways of doing physics and flirting. Unless you're one of my tutors or fellow students, in which case you better not talk physics or flirt with me, because you know what I'm actually like. The other big caveat is, don't rely on chat-up lines. Tell them what's in your heart. Your horrendous, festering, lonely, lonely heart. If you don't like it, you pick yourself up and you carry on until someone does. Be as kind as you possibly can be, and if it doesn't work out, at least you might have made the world a slightly better place while you were there. Okay, so without further ado, the first chat-up line. Are you in the early stages of stellar formation? Because things are about to get hot and heavy. One of my favourite parts of physics, a lot of people's favourite part really, is the life cycle of stars. The life cycle of humans is pretty boring by comparison. I mean, your folks meet, maybe one of them forgets to use protection, you get born, you go to school, you get a job you don't like, you meet someone else and maybe have a few kids of your own, and then before you know it you're dead. And after you die, eventually everyone turns into the same thing, a skeleton or maybe some ashes, which is not the case with stars. They can die in such dramatic ways as to tear holes in the fabric of space and time itself. They can turn into objects with magnetic fields strong enough to kill you from 1,000 kilometres away, by bending every single one of your atoms out of shape, and rendering any chemical reaction that supports life impossible. Magnetic fields strong enough that if we had one on Earth, it would wipe credit cards on the moon. They can collapse into objects so dense that a single teaspoon of their matter weighs as much as a mountain. In other words, they die in such over-the-top ways that Nicolas Cage would meekly hand over his bad-acting crown. And while they live, stars are awesome in scale and magnitude. And when they die, they do us all a favour, because they flood the universe with the building blocks that make up everything else, including most of the elements in your body. Plus, we think about people as the natural building blocks of the universe. We're really very self-centred. Really, what we are is a tiny, weird, bizarre, annoying, self-aware fraction of the matter in the universe. But matter doesn't like turning into humans. It's very difficult and complicated. That's why there's so few of us. If you leave matter to its own devices, to obey the laws of physics, it turns into stars. They are the building blocks, the natural units, the shimmering, glorious and beautiful products of the laws of physics. And we're just some weird, complicated, but ultimately cosmically irrelevant offshoot. So yes, stars are better than people. Luckily there's enough in our galaxy alone for each of us to have 14. Dibs on the sun. What's really amazing is that physics actually works pretty well in outer space. I say this because a lot of fundamental physics is really difficult to see here on Earth. For example, you probably all know Newton's first law, which says that if you give something a kick and it flies off with a certain speed, it will carry on going forever at that speed until something else stops it. Which is amazingly counterintuitive to us living here on Earth, because that's not how our world works. We kick things and they either complain or they move for a little bit and they stop. The ancient Greeks used to think that the natural path for objects to travel was a parabola, an arc downwards. And it makes sense because if you throw a javelin or a wheel of cheese, that's what it will do, it will arc downwards. They didn't realise that there was another force acting on it the whole time, air resistance. They didn't realise that the atmosphere makes it more complicated, that there's so much friction and drag, and so we can't see how physical objects naturally behave. But if you threw that wheel of cheese in space, it would go on forever, until something like gravity influenced it. Nowadays, we know that in everything that happens, energy and momentum, that is, momentum is a measure of what direction stuff is going in and how much stuff is going that way, are conserved. But it's not at all obvious to see that on Earth. It seems like energy is dissipated, for example when two objects collide. In actual fact, it's turned into heat energy that's difficult to measure. It's still there, but we can't measure it so easily. But way out in space, things are in a way less complicated. Stuff is free to fly around, being pulled in all various kinds of direction by gravity and electromagnetic forces, but in ways that are simple to model and understand. So we can get a pretty good idea of how stars might form just by saying, OK computer, what happens if we put all this gas and dust in this one location and just let gravity and electromagnetism do its thing? So for stellar formation, we have a pretty good model. It's less complicated than some of the processes that occur on Earth. And what we think happens is something like this. In some regions and galaxies, there's more dust and matter than in other regions. The nature of gravity is such that everything is attracting everything else. So if a region starts off dense, it gets more and more dense and collapses over time. Now these regions, they start off incredibly cold, around 10 Kelvin. The Kelvin scale of temperature is defined so that the 0 is as cold as anything could get, and 1 degree is the same as 1 degree Celsius. So 10 Kelvin is around minus 263 degrees Celsius, much colder than liquid nitrogen. The background temperature of space, although it's tricky to define, is around 2.73 Kelvin. So not hot and heavy to start off with. The seeds of this gas and dust, they could be former stars, although it's worth pointing out that the universe is actually fairly young compared to the lifespans of some stars. So the sun is going to be stable for about 10 billion years, but the universe is about 14 billion years old. So it's not like the air that you breathe that may have been inhaled and exhaled many millions of times. There might not have been that many stars before the current generation. The one thing to take away and remember about stars is that they're stories of force balance and force imbalance. When the forces are balanced, things can stay like they are for a little while. But as soon as they become imbalanced, something about the star has to change to compensate. We can understand that if two people are pushing on an object with the same amount of strength, it won't move. But if one of them gives up, then, it's the end of the tug-of-war game and everything collapses. Usually in the case of stars, the star will change its size to compensate. And we'll see this time and time again. So, the gas and dust collapses towards its centre of mass and we get a denser cloud. This situation is fairly stable, because as the gas collapses, its gravitational energy is being turned into kinetic energy. And this means that it heats up. It therefore has a certain pressure. And this pressure works in the same kind of ways as pressure in an air balloon does. All of the molecules of gas are whizzing around at speeds due to their internal temperature, and they collide with the walls and push out on them. That's what keeps an air balloon inflated. It's all the molecules of gas pushing on the walls. So for a while there's a balance. New gas particles get dragged in by the gravity of the cloud, but they're pushed back by collisions with the hot, dense core. Eventually, though, the cloud gets too heavy at a mass that's called the Jeans mass, and gravity can overcome this pressure. Now there are loads of theories as to how this happens, how the star gets up to the Jeans mass. So maybe a nearby supernova can throw a whole bunch of hot matter at the cloud, which could disrupt this balance. It's even possible that the gravitational effects of distant galaxies colliding with each other could disrupt the gravitational equilibrium. Stuff could fly in from elsewhere and cause an overdensity. Or there could just be fundamental instabilities that we don't really understand that cause the cloud to collapse. So, yeah, you could get another chat-up line out of this if you wanted to. You're hot enough to push me over the Jeans mass threshold or something like that. But of course it's not named after denim, even though that is the superior fabric, but a scientist, James Jeans. And as well as his considerable contributions to stellar physics, astronomy, cosmology and quantum physics, he also had an interesting philosophical perspective on science. And I'm including it here because it totally contradicts something I said earlier. And it's always good to contradict yourself if you can. That's what we call fair and balanced. Jeans, in his 1930 book The Mysterious Universe, wrote, quote, "The stream of knowledge is heading towards a non-mechanical reality. The universe begins to look more like a thought than a great machine. The mind no longer appears to be an accidental intruder into the realm of matter. We ought rather hail it as the creator and governor of the realm of matter." End quote. This is literally idealism. His philosophy, probably inspired by the burgeoning field of quantum mechanics, that consciousness is somehow a necessary part of the universe, that it, in a sense, defines the universe. He loved to put things in these poetic terms. He once said, "It may well be, it seems to me, that each individual consciousness ought to be compared to a brain cell in a universal mind." Now, I can't quite subscribe to this philosophy all the way. Maybe it's just the case that I'd rather think of humanity and our consciousness as a sort of bizarre, weird cosmic accident, for my own personal reasons. Maybe it's too tempting to think of physics and the laws of physics as the things that continue to occur without the presence of humans or any life. But quantum mechanics might contradict that, of which more later in a future episode. One thing I will get out of the way early while I'm on this tangent is to talk about how our understanding of science relates to our philosophical beliefs and our personal beliefs. This issue is overplayed sometimes. I know plenty of physicists, far smarter than I can ever hope to be, who are religious. I'm not, but I can see how one can, with a religious perspective, look at aspects of physics and ooze your confirmation bias all over them, in just the same way as I look at aspects of physics and use them to back up my own beliefs. You see what you want to see, and unless we find heaven in the heart of some active galactic nucleus, or we discover that the universe has a copyright logo somewhere, we're not going to answer this kind of question with science. I think the human brain is too good at compartmentalising these things. And thank goodness, because most of us need a little bit of irrational belief, or at the very least, beliefs for which we can't find conclusive evidence in our lives, to find the will to get out of bed in the morning. Okay, so, thanks Jeans for that tangent, and for working out when hot clouds of gas are going to collapse. Because things are finally starting to get hard and heavy. That mass is actually thousands and thousands of times heavier than the Sun. So what happens is that the big cloud breaks up and fragments into lots of various little subclouds that continue to collapse. And eventually, each of these little cloudlets becomes a rotating sphere of gas. Wait a minute, why rotating? Well, one of the most universal laws of physics that we know and understand now is that rotating things like to keep rotating. That's conservation of angular momentum. Whenever physicists don't understand what's going on in a system, they usually say, okay, energy, momentum, and angular momentum all have to be conserved. This happens in pretty much every process that we know about, so it's usually a good bet. A great analogy people like to use for conservation of angular momentum is an ice skater spinning. Every time I go ice skating I usually fall on my bum, which I think is still better than falling on my face. You know, it's not great, but it needs to be protected, right? As the ice skater pulls in their arms, they speed up and spin faster. This is because things have more angular momentum if they're further away from the centre of rotation, or if they're moving faster. So pulling in the arms means they're closer to the centre of rotation. And for angular momentum to be conserved overall, the skater has to spin faster. Because of angular momentum conservation, almost everything in space is rotating around something or other, usually lots of things at once. Of course, we're familiar with this because our moon is rotating around us, and the planets are rotating around the sun. But the sun and most stars in the galaxy are also rotating around the galactic centre, and this is true for clouds as well. And since the clouds that are closer to the centre are moving more quickly, In a big cloud, some of the gas is whizzing around faster than the others. So if you imagine you're a gas molecule in the centre of the cloud, if you look towards the centre of the galaxy, you'll see that those guys are moving faster than you. And if you're looking backwards, away from the centre of the galaxy, you'll see that they're moving more slowly. So, relative to you, from your perspective, you can see them almost rotating around you. And this is what means the collapsing cloud has angular momentum. But nothing can destroy angular momentum, which means that the cloud can't collapse directly onto its central point, at least not straight away. I mean, you can imagine this, right? If things are actually on the axis of rotation, they'd have to be spinning almost infinitely fast to conserve their angular momentum. So what actually happens is that an accretion disk forms. This disk lets matter flow to the centre more slowly, conserving angular momentum. Some of it is going to spiral in, and some of it is going to transfer its angular momentum outwards and spiral outwards. So angular momentum overall is conserved, but you can still get things to collapse into a more dense, spinning object. So when our star forms, it's going to be spinning in some direction that will be set by the line to the centre of the galaxy. And the fact that the star is spinning you should always remember, because that's super important for what happens to the star when it dies. So our big cloud is collapsing and getting hotter and denser. The dust around the star is radiating away most of the energy released from the collapse, and it's starting to get a little bit warmer. So maybe now it's 80 to 100 Kelvin compared to 10 Kelvin before. At each stage, the star will accrue a bit more matter, collapse a bit further, and heat up a little bit more. The central part of the star starts to get dense enough that it becomes optically thick. Now that means that radiation can't just freely flow out without hitting other molecules and atoms. So the radiation has to come from the outer layer star. And this process continues for around 1 million years. The core heats up so that its pressure is high enough to support the star. More matter accrues through gravity, so the core heats up more, and so on. Things are getting hotter and hotter, and heavier and heavier. Now eventually the star is producing enough radiation streaming outwards to push away its envelope of gas and dust. And if there were no other processes, things would carry on like this. The star would collapse and heat up until it couldn't collapse anymore, and just became a brown dwarf. It's kind of like a planet, but without orbiting any other star. Jupiter, for example, is still collapsing and heating up, just very, very slowly. The reason that Jupiter is hotter than a lot of the other planets on its surface is partly because it's shrinking, and the gravitational energy of its shrinking is being converted into thermal energy on the surface. But luckily for us, there are other processes that take over, namely nuclear fusion. Time for some basic nuclear physics. So a nucleus is around 10 to the minus 15 metres across. That's 1 divided by 1 with 15 zeros after it. Tiny. Scientists call this a femtometer. But the nuclei contain protons and neutrons, and the protons are positively electrically charged. So, like charges repel, and you've got a ball full of positive charges. And like gravity, the electrical force is stronger the closer the two objects get together. So the protons, squeezed together across tiny distances, are being pushed apart by an enormous force. How do they stay together? Well, gravity won't cut it, not even close, not by a long shot. So what's required is a strong nuclear force, which scientists have called the strong nuclear force. But it can't act over very long distances. Otherwise you can see what would happen, right? All of the protons and the neutrons would eventually clump together in a massive nucleus, and that would be everything that existed, which would be weird, and doesn't agree with what we observe. So the strong nuclear force can only be important on really small length scales, around a femtometer or the size of a nucleus. It's kind of like me in a way. From a long distance I can basically be ignored, but up close I'm irresistibly attractive. But if a nucleus gets too big or has too many protons, the strong force won't be enough to keep it together. So that's why we only have stable elements up to a certain atomic number. The nucleus can only get so big, and then the strong force, which can only reach so far, strains to keep it together. And that's why these heavier elements are radioactive and keep losing bits of their nuclei. Now if the temperatures are hot enough, electrons are going to be freed from atoms, giving us just bare nuclei. And if we can push these close enough together, against their electrical repulsion, the strong force will take over. And under certain circumstances, the nuclei can combine. Now generally in physics, if a process releases energy, it's allowed to happen, and it does tend to happen. And the processes that require energy will need some input from the surroundings. So if the nuclei combining can make them rearrange in a way that releases energy, then it can happen, and energy is released. And that's nuclear fusion. Nuclear fusion is responsible for almost all types of energy on the Earth. Seriously. It powers the sun. Coal, oil, natural gas, they're all formed by dead creatures that absorbed energy from the sun, or ate plants that absorbed energy from the sun. Even the wind is driven by the temperature differences that are caused ultimately by the sun. The nuclear elements in the Earth's crust that decay to keep it warm and provide energy in hot springs, or that we dig up or decay from ourselves in nuclear fission reactors, they're also formed by fusion reactions in the sun in supernovae. Hydroelectric power generates electricity by letting water run down a hill, but the water often gets up there in the first place because of rain, which is evaporated by the sun. Pretty much only the tides I can think of are things that don't depend on nuclear fusion for energy. So it's a good job that fusion is a big deal. Otherwise, I guess our main source of power would be rolling rocks down hills. But nuclear fusion requires things to be really hot and really dense. Turning to our star, the core temperature has to be around 10 million Kelvin for fusion to start to occur. So this translates to a certain amount of mass that has to collapse in order to get the densities and temperatures up high enough. But at the point of collapse when nuclear fusion starts, the stars can be at a range of different masses. They can be from around 1/10 of the mass of our Sun, up to around 100 or 200 times the mass of the Sun. If the star's too small, it becomes a planet like brown dwarf. If it's too large, radiation pressure tends to blow away a lot of that excessive mass, so the photons are produced in the centre of the star, they push all of the mass away. Now when hydrogen fusion begins, it causes a vast amount of heat energy to be released, and this blasts away the outer layers of gas and dust in the star. And the star usually expands to much, much greater than its original size during this period. Now, finally, when the star is fusing hydrogen together that powers it, we have what's called a main sequence star. By the way, that means the phase beforehand is called a pre-main sequence star, or sometimes a PMS object, which I find hilarious because I am immature. So our Sun is a main sequence star, and the main sequence is pretty stable because there's a lot of hydrogen to fuse. So the Sun is estimated to live for around 12 billion years in its hydrogen-burning phase. So there's plenty of time left if you still want to learn to play the piano. Next episode, we'll talk about how stars evolve and how they die. In the meantime, you can get in touch with me via PhysicsPod on Twitter. You can go to our website at physicalattraction.libsyn.com. And I'm sure if you see me on the street, you could also say hello, or email us at physicspod@outlook.com. Our theme music is The Love God by Martini Bomb, and you can find their work for free online.
Would have regarded as a peer. Hi, folks. Want to hear something funny? I'm cursed. An abnormal sexual magnetism.